So in this clip I will go through a number of things which will summarize some bits of what you've done so far in econometric methods and bits which are just relevant to keep in mind as we continue for the rest of this course. Before we start, let's run a regression. After all, most of it is about this. So we're gonna run a regression using data in the following spreadsheet, MROZ.xls. That will also be in the Blackboard folder from my first lecture. And let's just firstly have a quick look at what the data in this file are. There will also be a MROZ.ds description file. These are data for a number of employees, and they're all female employees, 753, and here we have a list of variables, for instance how many hours they worked, what sort of wage they have, how old they are, whether they have kids, and all sorts of interesting things. So that's the sort of variables we have, and I have this file copied into my MATLAB folder. You can firstly just open the Excel spreadsheet, and here you can see we have 753 observations. In that spreadsheet there's no header file. You have to read this in conjunction with the DS, the description file we just looked at. And here are all the data. Okay, let me close this again. Move this away. So the first thing we're gonna do, I will write a little MATLAB file called stateofplay.m. You can of course replicate that yourself. I will not put that on Blackboard. You will have to do that yourself, but that's very quick. We will use the XLS read command to upload the data. They are in mroz.xls, and if you've done any MATLAB, you will know that this function will hand back three things: the data, the text data, and then the raw data. We've seen there are no headings, so there will be not much difference between the data and the raw element, so we can import this. Then I also have here the ols.est.m function, so that means we will be able to run a regression. You will know that all we need to do is we need to call that function. We need to hand in a vector for the dependent variable and a matrix for the explanatory variables, and if we want to print the result we have to enter (1). You recall that you can see what is required by typing help ols.est, and here you'll get little descriptions of the required input. So y, x, and then output 1 if we want the results printed. So that means all we need to do now is we need to define what y and x are. So for that we need to go back. So all our data, the spreadsheet is basically now in data. So what we want, let's first write this down. So what we want is the following regression. We want to regress log wage for the ith observation on a constant beta1 plus beta2 times the age, the ith employee, plus beta3 times education of the ith employee, plus beta4 times the experience of the ith employee, plus an error term of the ith employee. So before we continue, what we're gonna let's do exactly that. So we want log wage, request on age, education, and experience. Let's go back to MATLAB. So we basically now want here we need to find out in which column we have log wage. So let's go back to our description file. L wage, that's the 21st column. So we will type data, all rows, 21st column. So then we want a matrix with explanatory variables. Let's use a constant. So once, that's in a minute we need to say how many rows we want here, one column, or how many observations, n. So we will soon have to define what n is. And then we want age, education and experience. So let's first look for age. Which column is age? In age is column 5, education is column 6 and experience is column 19. So 5, 6 and 19 we need. 5, 6 and 19. Semicolon. Now we want to know how many observations we have for our constant, so we'll just say size y, 1. So that will test how many rows we have in our dependent variable. So if we run this, of course we get a little mistake. I think I may not have cleared it before I did something else. Let's hope that works. Yeah, okay, so that works. So what we have here is the regression output. We have 4 explanatory variables, 3 variables plus a constant, so we have 4 rows in our regression output. We'll get back to this in a minute. Okay, so let's go back to our theoretical model. Firstly, we'll want to restate this in matrix form. So basically we have y, x, beta plus u. So this is now our usual sort of matrix form. We have y, our dependent variable, which is going to be an n by 1 vector. Let's actually quickly check how many observations we had. Observations 4 to 8. Okay, that was 4 to 8 because we had missing observations. The regression code automatically excluded missing observations. So here we go. Now this x matrix, that was a observations n times k. Now, and beta was k by 1. It's really good to understand the dimensions of these terms. And u was n by 1. And of course in our example k, how many columns did we have in x? That was 4. So x was basically a matrix that included a constant, then a vector of values which were the age, another vector of values which were education, and another vector of values which represented experience. So if we look into MATLAB, if we open X, this is exactly what we can see. Okay, a matrix with 4 columns. So now just a little bit revision of theory. Of course, you know from that model that our OLS parameter estimator was calculated as beta hat x prime x inverse, well, that x of course was this matrix, x prime y. Okay, so this formula you should know in your sleep. Now you also know that if the Gauss-Markov assumptions hold, then the following is true: the expected value of beta hat, I'll leave a little bit of space here, is equal to beta, and the variance of beta hat is equal to sigma squared x prime x inverse. Now, I left a bit of space here because what I want to put in here is a conditional on x. Okay, and you learned with Len that we had to put this in if we assumed that the explanatory variables were not necessarily fixed in repeated samples. So we treat them as random variables as well, and our results we state them as conditional on the observed x. Just give myself a little bit more space here. So, firstly, before we continue, I want you to understand the dimensions here again. That beta, this guy here, is going to be k by 1. Okay, and therefore the estimated, so that was our beta here, that was k by 1, and therefore we should estimate k parameter values. What about the variance of beta hat? Now this guy, sigma squared, that is the variance for the error terms. That guy is a scalar. Now x prime is going to be k by n, x is going to be n by k, so this entire guy is going to be k by k. The inverse doesn't change the dimension, so the entire variance for beta hat is going to be k by k. So you can think about this as a square matrix, okay, with k dimensions. So what we'll be interested in soon is the variance of the individual elements of this beta. Okay, so here if we have 4, if k is 4, that means we have actually 16 values in here, k by k. Now the ones we are mostly interested in are going to be these values on the diagonal. Okay, these are the ones we're interested in. These are going to be the variances for the individual parameter estimates. So that's going to be a 4 by 4 or a k by 1 vector. And these are the variance for the individual beta, for beta 1 hat, beta 2 hat, beta 3 hat. Alright, so let's see where we get these results. Let's see, we want to match these things to our regression output. So we shall just copy that across. So here's our regression results from MATLAB. I just now want to match sort of the values we have. So firstly, let's find beta hat. That should be as we know, a 4 by 1 vector. Now that vector we find here. So the first element is the constant. That is beta 2, so that is beta, that's going to be quite small. Beta 1 hat, beta 2 hat, beta 3 hat, beta 4 hat. So the first value is the constant, the second is the coefficient for age, the third to education, the fourth to experience. So that's the beta hat. Then next we want to find this vector of variances. Well, what you can see here is the standard, it says SE parameter, so that's going to be the standard deviations of the estimated parameter estimate. So what that basically is the square root of this guy, okay, and that's what you can see here, okay, so that's the term here. So that's important to understand. The question is now, what can we do with this? And very often what we want to do, of course, is we want to do inference. So what I'm now going to do is just a quick repetition of some basic inference in the context of this regression output. We'll do 3 examples. Okay, so first example is we want to test the following null hypothesis. Beta 3 is equal to 0 against the alternative that beta 3 is unequal to 0. Now, of course, beta 3, what does that mean? Beta 3 is the coefficient to education. So if that was 0, that would indicate that education plays no role in determining the wage, or more precisely, the log wage. So we know that what we need to do for a simple hypothesis here is we want to calculate a t statistic, and that's going to be the estimated value for beta 3 minus the hypothesized value divided by the standard error of beta 3 hat. So this value here, this comes from this null hypothesis. So in our case, that is going to be a 0. Okay, so that's going to be minus 0. Then we want the estimated coefficient for beta hat 3, that is going to be 0.1093 divided by the standard error of beta hat, that's 0.0142. So what is that? We'll just bring the magic calculator up. 0.1093 divided by 0.0142, that is equal to 7.697. 7.697. So to conclude, to make a decision with respect to the null hypothesis, of course, we need a number of additional things. We need to know at what significance level we want to perform this test. So let's use the standard value of 5%. We also need to know how the t-test is distributed. Now, you know that this is t-distributed with n minus k degrees of freedom if the Gauss Markov assumptions are valid and we also assume normality of error terms. Especially if we can't assume the normality, what we then of error terms, what we then know is that asymptotically, i.e. in large samples, this test statistic is going to be standard normally distributed. Okay, that's if the Gauss Markov assumptions are valid. So what does that mean? That means to get, for instance, critical values, we will have to go to the standard normal distribution, and that's what we'll do in a moment. Now, before we do that, we'll draw a little picture. When you do tests, it's always worthwhile drawing a little picture. We'll draw something that is supposed to be a standard normal distribution. Now we know that this has an expected value of 0. And we also know that our test statistic here is somewhere in the right-hand tail. But before we plot our test statistic here, in fact, you could do that before you calculate the test statistic, you have to write down a decision rule. And that decision rule will always contain the following part, or will always start like this: reject H0 if, and then something. Now this if we have to complete now. If we have a two-sided test statistic, we will reject the null hypothesis if we get very extreme test statistics, either very extremely positive or very extremely negative. The question is just what, so either somewhere here in the tail or somewhere here in the tail. The question is, what is extreme enough? Now that's why we need to find our what we call critical values. How do we determine the critical values? That's what we use the alpha for. Basically, we want the critical values to cut off alpha % from our distribution. Since we have a two-tailed test, we can see that from the alternative hypothesis, we will have to divide that alpha into both tails. So we will have a probability of alpha over 2 in this tail and a probability of alpha over 2 in this tail. So this probability of these red tails should add up to 5%. So we need to look for that value that cuts off 2.5% either in the positive tail or in the negative tail. So let's go to our distributional table. So here's a table, standard normal probabilities. This is the table you will get in the exam as well. So what we are looking for, what we have in this table is here you can see it, the probabilities that Z is smaller than a particular value, and what you see in here then is a probability. So with that in mind, what is it we need to look for in this table? So we want this table, we want this guy here to be 2.5%, but we know that the probabilities we find in the table are the probabilities, let me do this in green. If we read off a certain value, we find the probabilities of the entire probability distribution function up to that value. So if we want 2.5% in the right bit here, how much do we want in the green bit? That green bit, by the way, includes this one here. We then need 0.75 in the green bit. So we go to the normal distribution table. We need to find 0.975 somewhere here, and actually you can see here we have exactly 0.975, and that value, which cuts off 97.5% to the left or 2.5% to the right, is 0.96. Okay, sorry, 1.9, and the second digit is 6 up here. Okay, that cuts off this value. So we know the critical value here is really 1.96, and since the normal distribution is symmetric, this value here is negative 1.96. Therefore, reject H0 if our t-stat, if t is either smaller than 1.96 or t is larger than 1.96. So with that in mind, we can make a decision, because our particular t-test is way off over here, off the screen in fact, and therefore the decision is we reject H0 applying this rule as t is larger than 1.96. Okay, so we reject H0. So let's continue to the second example. Second example, we're going to test the following null hypothesis. Beta 4 is smaller or equal to 0.01 is the null hypothesis, and the alternative is beta 4 is larger than 0.01. Beta 4, that was the coefficient for experience. So someone basically claims that the effect of experience is larger than a certain value, and we put that in the alternative, and the null hypothesis is the complement of this. Now before we do any calculations, I want to draw the picture again. So here's our picture. Let's think. Basically, it's always actually a good idea to first write the decision rule. Actually, before we do that, we'll use a different alpha. Let's use alpha of 1%. So the decision rule is going to be the following. Reject H0 if. Now, since we have a right-tailed test, we will only reject, let me first write down what the test statistic in principle is, beta 4 hat minus beta 4 divided by the standard error of beta 4 hat. Again, this beta 4 here is going to come from the null hypothesis, so it's going to be 0.01. Now, in what case will we reject the null hypothesis? So we will only conclude that beta 4 is indeed larger than 0.01 if we have this time a sufficiently large value for beta 4 hat, and therefore a sufficiently large value for beta hat. So we will only reject if we land somewhere in the tail here. So we want this critical values, and since we have a one-tail test, we are looking for the value that cuts off alpha, the probability alpha here. So let's find out what that is. So we want, if we want 1% in the tail, we want 99% on the left hand side. So we need to find the value here where we have 99%, and the value that is closest to that is this one here. Okay, not exactly, but very, very close, much further away than the next two. The value that gives us that probability is 2.33. Okay, so our critical value here is 2.33. Therefore, reject H0 if t is larger than 2.33. So now we continue to calculation. We know it's going to be negative 0.01. That's from the null hypothesis. So we need beta 4 hat is 0.0163. 0.0163. That was this value here, and the standard error is 0.0046 divided by 0.0046. So let's get the magic calculator. In the numerator we have 0.0163 minus 0.01, and then divided by 0.0046. And what we get is 1.37 approximately. 1.37 equals 1.37. So that value is about here. 1.37, remember 0 is here, therefore we do not reject H0. So there is not sufficient evidence to reject the null hypothesis and conclude that beta 4 is larger than 0.01, although the estimated value beta 4 hat is of course larger than 0.01. But recall, the hypothesis is on the unknown coefficients, not on beta hat. We know beta hat, that's 0.0163. But how can we use beta hat to draw conclusions about beta, the unknown beta? That's what we do here. So lastly, the third test we're gonna do is gonna be a multiple hypothesis, and here the hypothesis is gonna be that beta 3 and beta 4 is equal to 0. What does that mean? Let's go back to our model. That implies that both education and experience are insignificant. The alternative hypothesis is that beta 3 and or beta 4 is unequal to 0. So you'll recall the type of test statistic you need for this. It's an F-test, and how this is calculated is residual sum of squares of the restricted model minus residual sum of squares of the unrestricted model divided by the number of restrictions divided by residual sum of squares of the unrestricted model divided by the degrees of freedom of the unrestricted model. In our case, the degrees of freedom is n minus k, and in our case k was 4. So before we conclude the calculations, just draw the distribution again. Now we know the f-stat is f calculated with r and n minus k degrees of freedom. F distributions are defined on the positive scale only. Not important how exactly it looks. Let's use an alpha of 5%. Okay, so before we do anything else, we write the decision rule, and that is reject H0 if. Now, the restricted model is going to be the model which implements this restriction, beta 3 and beta 4 is equal to 0. That basically means we run a regression of log wage only on a constant in age, not on education and experience. Now, this model is going to fit the data less well than the model with all explanatory variables. That means our restricted residual sum of squares is going to be larger than the unrestricted residual sum of squares. That means our test statistic is going to be positive. The question is that difference in residual sum of squares, or the difference in fit, is that significantly large to reject the restriction? And if it's large enough, we will reject H0. So basically what we need again is a critical value. Okay, basically we will reject H0 if f is larger than a certain critical value, if we are over here. Again, we need to find from the distribution that value that cuts off alpha % of that distribution. Now for the calculation, so what we need to know, let's find the critical values. We need to find what the degrees of freedom is, r and n minus k. In our case, r is going to be 2 because we have 2 restrictions, and n minus k, what was n? N was 428, okay, that was n, and k, so 428, and k was 4 minus 4, so that's 424. So let's go to the f distribution table. That should be somewhere on here as well. That's chi-squared. F, that's for 5%. We want degrees of freedom 2. That's the first one. Number of restrictions 2. So we are looking at the second column. And 428. Well, the maximum value here is 150. So we use that. So the critical value is 3.06. Sorry, oh, I hope you could see what I drew before here. 3.06. That's the critical value. So we reject H0 if f is larger than 3.06. So let's do the calculation. Let's see what we have. I'll do it down here. So f equals, we have estimated a model already up here. That included all 4 elements. So that is the unrestricted model. So what do we need from here? From the unrestricted model, we need the residual sum of squares. Actually, we already know the number of restrictions. That is 2. And n minus k, we just calculated that. That was 424. So we know that already. Then we need restricted minus unrestricted residual sum of squares and unrestricted residual sum of squares. So one of the outputs in our model is the RSS. So we calculated the unrestricted sum of squares. Let's see if I can. No, it didn't work. Anyway, so that was, let me check again, 190.156. Okay, that was the 190 and 1565. 190 and 1565. And down here as well, 190, 1565. But there's still a guy missing here, okay, and that is the residual sum of squares of the restricted model. So we need to estimate that. We need to go back to MATLAB, and what we now need to estimate is another model. Let's say, let's define another XR, and in here we only want the first two elements, okay? And then we estimate using XR, we run our regression, and what we get now, of course, we only get two coefficient estimates for the constant and that first variable, which was h, and the residual sum of squares is 2226539. So 2226539. Okay, so now we need to calculate what that is, and it is 36.23 approximately. Now that is clearly way over here in the tail, and therefore we will conclude that we reject H0 as f is larger than 3.06. So that null hypothesis that education and experience are irrelevant is clearly rejected.